Welcome back. So this is lecture 16 in this course on Bayesian modeling. My name is Himanshu, and today in this lecture we are going to talk about Bayesian inference. So this is an introductory lecture to Bayesian inference. So how exactly we apply Bayes theorem in practice for drawing inference about the underlying generative process given some data. Okay. So in the previous lecture, uh, we talked about Bayes theorem, and we also saw a quick abstract example of how Bayes theorem can be applied in statistical inference. We will see it in more practical sense, how exactly we do it, and we will discuss each term in the Bayes theorem. Okay. So just to recap, the Bayes theorem was this: that if you have, let's say, mutually exclusive and exhaustive events a1, a2, a3, an, right, then probability of event a1 given b can be given by probability of b given a1 into probability of a1 divided by summation of this term, okay, summation of the numerator term across all mutually exclusive and exhaustive events. Okay, so across all ai's from I is equal to 1 to n. This was Bayes theorem, right? Now, in order to apply it in the context of statistical inference, right? So let us say in an experiment you have observed some data. Maybe let's call the data x. So this is the observed data in some experiment, right? Now there is some true generative process that has produced this data, right? So this data must be coming from some true generative process, but you cannot know what is exactly this true generative process. Only thing you can do is that you can infer the properties of this true generative process. And how do we make that inference? Well, we go through this route. We make some assumption that the observed data should be coming from a probability density function or mass function f of x theta, right? So this x is coming from f of x theta, right? Now, given the data, what we want to do, we want to infer that given the data, what is the true value of theta. Okay. Once we know the true value of theta, we can extend it to know what this true generative process might look like. Okay. That is actually the first step in inference, that we want to estimate true value of parameters of your probability density function, probability mass function that you assumed had generated your data, right? So given this data, what is the true value of theta that might have generated this data, right? And by extension, then you can try to infer the true generative process. Of course, there is second step in inference. Without that, inference is not complete. That someone else can make a competing assumption that this data comes from g of x lambda, right? Now, given the data, you will also estimate true value of lambda. So let's say the true value of theta is theta hat and true value of lambda is lambda hat, right? So the true generative process you are saying behind this data is either f of x theta hat or g of x lambda hat. So either of these two is the true generative process. Okay, then you will compare these two, that which one is better at explaining future data or unseen data. Okay, so we will put these competing assumptions to some test, that which one of these assumptions is better at explaining some future data or some unseen data. And that would, so let's say if this one turns out to be better at explaining some unseen or future data, then we'll say that this process is closer to true generative process. Okay, so that is the whole workflow of inference, right? Now, where does Bayes theorem comes into picture in all this, right? It comes into picture at this point. So the assumption we have made about our data, that our data comes from f of x theta. So x is the observed data, it comes from this underlying probability density function, right? Now you need to estimate true value of theta that might have generated this data. Okay, so this is where Bayes theorem comes in. So point here is this, that it is not necessary that theta would have only a single point value. Okay, theta could have its own distribution. Okay, and that's a theoretically different position we are taking here. So in frequentist inference, you often assume theta is a point value, but here theta is itself a random variable. So of course, we still want to go towards that point value. We still want to know exactly what point value theta would have, but there will always be some uncertainty in estimating the true value of theta. And that uncertainty can be captured if we assume theta is a random variable. We do not want to throw away that uncertainty, because every time when you have some data is just a limited sample from the population, right? Every time you have some limited sample from the population, it would tell you something about the theta, but it may not tell you everything about theta. So there will always be some uncertainty about the true value of theta, and we do not want to throw away that uncertainty, because that uncertainty is used for us, right? So for example, you collected some data x, and x tells you that, well, theta could be equal to 0.6, it seems to be most likely value, but theta equals to 0.5 is also a likely value. So the data could also very well come from this, the data could very well come from this as well, right? So it's very difficult to find a point value given a limited sample from the population. Right? This is always going to happen. The same data can be generated by this as well as this, right? If we just estimate a point value, let's say maximum likelihood estimate of theta, that's a point value, right? If we just estimate a point value of theta, then we are throwing away this possibility that this data can be generated by this as well, right? We do not want to do that. We do not want to throw away this information that the same data can be generated by different values of theta. But some values of theta can be more likely and some values of theta can be less likely. How do we capture this? We can capture this if we assume that theta is a random variable. Theta does not have a point value, but theta is a random variable. That's a much more reasonable assumption to make. So once we say theta is a random variable, then we are not interested in a point value of theta. Let's say some value like theta naught or something. We are not interested in point value of theta. What we are interested in is the underlying true distribution of theta. Okay, so rather than saying that you want to estimate true value of theta, what you would say now, that you want to estimate true probability distribution. This is a probability distribution. You want to estimate true probability distribution of theta. Okay, so rather than estimating a point value, we are interested in a true distribution of theta. So theta would have a true distribution, which would tell us that some values of theta would be more likely and some values of theta would be less likely. Okay, so assuming that this data x was generated by this generative process f of x theta, what is the true distribution of theta that would produce this observed data x obs, or this x, right? That is our goal, that we want to estimate this true distribution of theta. How do we estimate the true distribution of theta? That's where Bayes theorem becomes very important. Now, this true distribution of theta that you want to estimate, okay, this is actually conditional on the data that you observed, right? Because you already collected this data x, right? We want to estimate what is the true distribution of theta given that you have observed this data x. If you would observe some different data, let's say y, then the true distribution could look slightly different, right? So we are retrieving information from this data to infer the true distribution of theta, right? So that's why what we are going to estimate here, because we are estimating it based on data, right? So we cannot obtain exactly what is this true distribution of theta. What we are going to obtain is a conditional distribution of theta given the data. So basically we are obtaining what is the conditional probability distribution of theta given the data has already occurred, or we have already observed this data x. So that's why we are estimating probability density or probability distribution of theta given the data. Okay, so it's a conditional probability density. Now this can be calculated using Bayes theorem. So Bayes theorem would say that P of theta given x would be P of x given theta into prior probability of theta divided by total probability of x, which will be basically if theta is a continuous random variable, which would be the case in most cases, most examples. So this thing would be P of x given theta. Remember, we sum this numerator term multiple times across all values of theta. So here we will integrate it across all possible values of theta, right? So in the range of possible values of theta. This is what we can use to estimate true distribution of theta given this data. So it's a conditional true distribution of theta given the data. Okay, but let me explain what are the terms here, because you might be confused by this as well. This looks like a true distribution, but that is not the case. So let us see what it is. Right? This first term, P of x given theta, okay, you can call it probability density of observing this data given a particular value of theta. But what actually happens here is this, that this is not exactly so this is exactly the same term that is in your function, right? So you assumed a probability density function for theta. So in order to calculate probability density of x given some particular value of theta, you will use this function f of x theta, right? So what you are calculating here is the value of this function, the probability density function. You're calculating probability density of x given theta, right? But interestingly, the values that you are going to calculate here are will vary with respect to theta, right? Because you are going to calculate probability densities. For example, when you calculate this posterior distribution, you will calculate the distribution like this, right? So this would be a distribution P of theta given x. I'm talking about this LHS term, right? So this is a distribution of theta, right? So for different values of theta, how different values of theta are likely to generate this data. So it's a distribution. So on x-axis you have theta. Okay, so how this particular probability density varies for different values of theta, right? In order to calculate this, okay, you will calculate these quantities, both P of x theta and P of theta, for different values of theta, right? So you will estimate this quantity for different values of theta. Let's say theta 1, this will be f of x theta 1. You will also calculate it for theta 2, that will be f of x theta 2, right, and so on. Okay, so you are calculating this quantity for different values of theta. Okay, because data is fixed, data is known, so data does not vary. Okay, so data is, or let's say x, or the value of the random variable is known and fixed. Okay, so under that condition, if you want to draw a graph of P of x given theta with respect to theta, you can get a graph because x is fixed and known. So theta is the only thing that varies, so you can get a graph. What graph is this? What is this then? So, what quantity we are getting exactly, because it's a function of theta. This is exactly the likelihood function. We discussed this a couple of lectures ago. So, basically this is your likelihood function. So, the first term you see in this Bayes theorem formula here in the numerator, it's the likelihood function. P of x given theta, it's basically the likelihood function. It's not necessarily proper probability distribution, because you are not getting any distribution with respect to different values of x. X here is data, so it is fixed. You are getting different probability densities corresponding to different values of theta. So, actually you are getting likelihood of theta. So, every time you are computing this quantity, you are calculating likelihood that theta 1 would generate this observed data x, likelihood that theta 2 would generate this observed data x, right. So, this is the likelihood function. Okay. So, that is the first term in the numerator on the RHS on the right hand side. What is the second term? P of theta. See, P of theta does not have any conditional component. It looks like it's just the probability density of theta. It does not have any data term. What it is called is prior probability distribution or prior distribution of theta before seeing any data or before seeing the given data x. Okay. This is actually your belief, your assumption, or your prior information about the true distribution of theta. So, although you do not know what is the true distribution of theta, but before seeing any data, you can make a prior assumption that, well, I think that this parameter theta might be distributed like this. So, let us say most of the values would be between 0.6 and 1. Okay. So, you can make that assumption. Let us say when it is a word recognition experiment, you can say that most of the times the participant will be accurate in judging, in recognizing words against non-words, right. So, for that kind of experiment, you can say that theta, the underlying probability of producing a correct response, could be somewhere between 0.6 and 1. Okay. That will actually depend on the context. I just gave an example, but you can have some prior assumption, prior belief, or some prior information. Let us say from previous studies on the same phenomena, you can have some prior information that what the true distribution of theta might look like. So, this is our assumption about the distribution of theta, about true values of theta. Okay. So, this is called prior distribution of theta. You have already seen P of x given theta, which we are calling the likelihood function. Okay. There is more common way of writing this likelihood function, which makes this much more clear and straightforward, that this is actually a likelihood function, not PDF, which is this, that rather than writing it as P x given theta, P stands for probability density, you can write it like this, likelihood of theta given x. That is it. You can write it like this. So, it is a likelihood for any particular value of theta. So, how likely is a particular value of theta to generate the data? So, likelihood of theta given x. This is just another way of writing the same term. So, this is much more transparent. It directly tells you that you are dealing with the likelihood function here, right. So, this is the likelihood function. The term in the denominator, which is, you can say, the total probability of data or the marginal likelihood, it is given by this. Basically, you are integrating the numerator term with respect to theta. So, across all values of theta, this is called marginal likelihood. Okay. This is actually coming from law of total probability. Marginal likelihood would be just some numeric value. So, let us say it could be 18 or something. Okay. It's going to be a constant. The function of the marginal likelihood is to ensure that this term, okay, so in right hand side you are multiplying this likelihood and prior density. So, this thing, if you do it across multiple values of theta, and it becomes a proper probability distribution. So that the output that you will get out of this, okay, it becomes a proper probability distribution, because we want that our posterior distribution is a proper probability distribution. Okay. So this marginal likelihood, which is just a constant, so we are dividing it by a constant, it ensures that the area under the curve is equal to 1. Okay. And we discussed one interpretation of this, which is that it is giving you, in a way, total likelihood of generating this observed data x given all possible combinations of your parameter values, right? Now the left hand side term is then p of theta given x. So we are trying to estimate true distribution of theta conditional on the data, the observed data. So given that we have already seen the data, what is the true distribution of theta? So this is called posterior distribution of theta. Okay. So P of theta was prior distribution of theta. So this is before seeing any data. And this is posterior distribution of theta. So basically after seeing the data. Okay. So actually it tells you what are the true values of theta given this data and your prior assumptions. So what values of theta might have generated the data, and gives you distribution, which values of theta would be more likely, which values would be less likely. Okay. So this is the posterior distribution. Okay. So in short, you can write that the Bayes theorem can be written like this, that the posterior distribution of your parameter, let's say theta, is likelihood of theta into prior density of theta divided by marginal likelihood. Okay, that's how the Bayes theorem works, right? So our goal is to estimate the posterior distribution of theta. So we want to estimate posterior distribution of theta given the data, right? We want to estimate the true distribution of theta given this data, right? So that is our goal. And how do we do this? We first calculate likelihood function. So given the data, you can calculate the likelihood function. Given the data and the assumption, basically the PDF, you can calculate the likelihood function. We have seen this in one previous example in a previous lecture, right? Then you multiply likelihood function with the prior distribution of theta, and then you divide it by the marginal likelihood, which is a constant term. Even if you ignore this constant term, you would get an approximate posterior distribution of theta. It would be just unnormalized. The area under the curve won't be equal to 1, but it would contain almost same information. Okay. So this is how you can write the formula for, basically you can calculate the posterior distribution of parameter theta given the data x. Okay. So in order to calculate this, it requires us to, a step by step inference process would be like this, that first make assumption about the true generative process. Okay, so you need to make two kind of assumptions here. So first is assumption about the true generative process. Okay, so what is the generative process, underlying generative process that might have generated your experimental data x, right? So we used to write it like this. Okay. Let's say you assume that it is x comes from a normal distribution, then you would like it like this: x comes from normal mu sigma. Okay, so that's your assumption about the true generative process, right? In practice, we will be calling it the likelihood assumption, because the purpose of this assumption is exactly to calculate the likelihood function. We will see in practice. So we will be calling it likelihood assumption. So that's the first kind of assumption you need to make. So what is the underlying distribution of the outcome of your random variable or outcome of your experiment? Second, you need to make prior assumption. So what is the prior distribution of theta before seeing any data? right? So let's say you assumed x comes from normal mu sigma, right? What are the parameters here? Mu and sigma. There are two parameters. So you need to make prior assumptions about both mu and sigma. Let's say mu comes from P of mu. You can assume any distribution for this. Let's say you assumed mu comes from normal 350. Okay, so that's the prior assumption of mu. What you are saying here is that the mean parameter mu lies somewhere between 200 and 400. So that's your prior assumption. You can also make some assumption about sigma. Let's say it comes from truncated normal distribution between 0 and 50. What you are saying is that likely value of sigma is between 0 and 100. Okay, it cannot be negative. It always has to be positive between 0 and 100. Right. So the first thing you need to do is make assumptions. That's step one. Once you have made assumptions, then you will of course collect data. So second is basically get data or collect data. And let's say the observed data is y obs. Okay, so let's say this is the observed data. Then you can go to step 3 because now we have data. So now what you can do, you can draw your likelihood function or you can calculate likelihood for different values of theta given the data. So you can draw a likelihood function. So let's say this is your likelihood function. Then you can calculate your prior density of theta. Okay, so you know prior densities of mu and sigma. So you can calculate the prior density of theta. In this case, mu and sigma. So you can write mu sigma here. So prior density of mu and sigma. So you can separately calculate it for let's say mu and sigma. Okay. So once you have likelihood and prior, then you just need to multiply them and you can approximate marginal likelihood or calculate marginal likelihood using some method. Then your posterior of let's say mu sigma given the data is just that it is the likelihood of mu sigma given the data, prior density of mu, prior density of sigma divided by marginal likelihood. Even if you ignore this, you will get unnormalized posterior distribution if you just multiply them for each value of mu and sigma, right? So that's how you can calculate posterior distribution step by step. In the next lecture, we will implement all these steps in R so that we know in practice how to calculate posterior distribution of any parameter given our likelihood and prior assumptions and the data. All right, thank you so much. So this was an intro to Bayesian inference and how to implement it in practice. In the next lecture, we will see model building in the Bayesian framework step by step. All right, thank you very much.